All right, everyone, it's Mr. Itty back with yet another video. So today, guys, we're going to begin Unit 7, which is on equilibrium. So our topics today, what equilibrium is, and then we're going to talk about the equilibrium constant. So dynamic equilibrium is the condition for a chemical reaction in which the rate of the forward reaction is equal to the rate of the reverse reaction. And the two words here, guys, that I want to point out are very important here is the rate. Okay, so it's the rates of the forward and reverse reaction that are equal to each other. Now, this does not necessarily mean that the concentration of the reactants and products have to be equal. Okay, in most cases, they are not because, again, equilibrium is when the rates are equal to each other. Now, with that being said, is it possible that the concentrations could be equal to each other? Yes, there are cases when they would be, but they don't have to be, and I can't stress that enough. When equilibrium is reached, guys, next important point here is that there will be no change in concentration, okay? So, as I just got done saying, the concentrations of the reactants and products do not have to be equal at equilibrium because it's the rate of the forward reaction is equal to the rate of the reverse. With that being said, though, once equilibrium is established, okay, then the concentration will no longer change. Okay, so that's important. Let's continue on. So let's look at this particle diagram for the equilibrium of hydrogen gas plus iodine gas yields 2Hi. Now, the way that you can tell that we're looking at an equilibrium, everyone, is that we will have a double arrow indicating that there is a forward and reverse direction. So this is synonymous with looking at equilibrium. And now let's take a deep dive into the equilibrium of H2 and I2 using this particle diagram. So you'll notice, guys, at A is at the initial concentration of the reactants of H2 and I2. Then B, you'll see 15 minutes or so has elapsed, or 15 seconds, however you want to break your units into, has elapsed of these particular molecules reacting with each other. You'll notice that they have produced 4 molecules of HI at this point. In C, a half hour later, you'll see that 8 molecules of HI have been produced. And then at D, 45 minutes later, 8 molecules of HI are still produced. Now, the question is, well, when was equilibrium reached in this particle diagram once we checked in every 15 minutes? And that would, of course, would be at point C. Now, the reason why it's at point C, folks, is because if you take a close look, 8 particles of HI were produced, while there are 4 molecules of H2 and 4 molecules of HI, respectively, still in the reaction vessel. Now, when you compare that to picture D, or point D, at 45 minutes, it's the same amount of particles in the vessel, except, of course, the particles have shifted somewhat because they're, of course, moving around. Well, the equilibrium then was reached in point C because the concentration did not change from point C to point D. Okay, and that's exactly what the graph below this is illustrating, is at that half hour mark, the rates of the forward reaction, the rates of the reverse reaction are equal, which means dynamic equilibrium has been reached. You'll notice, guys, that the rates of the reactants initially start off fast, but gradually slow down as the reaction proceeds. Conversely, the rate of the HI kind of speeds up throughout the entire reaction and until, of course, dynamic equilibrium is reached. Now, dynamic equilibrium is reached right where I'm about to draw this pink line, all right? And at that point thereafter, the concentrations of our products and reactants will no longer change. However, it's not, but you'll notice that the concentrations are not equal to each other. I said that the concentrations did not change, so I'm using my words very specifically here. But what has been equal is the rate of the forward reaction is now equal to the rate of the reverse. So if we were to just make a conclusionary statement here, what happened in this picture, right? what we would say is as the reactants reacted, right, the rate of the forward reaction slows down while the rate of the reverse reaction speeds up. And of course, that would happen until dynamic equilibrium occurs. That would be when the rate of the forward reaction is equal to the rate of the reverse reaction. So in this case, the forward reaction would be, of course, H2 reacting with I2. And then the rate of the reverse reaction was when you take two molecules of HI and the two molecules of HI react with each other, reproducing the products. Okay? That's how we would interpret this graph here. Now, let's continue on. Let's talk about the equilibrium constant K. So the equilibrium constant K is defined as the ratio at equilibrium of the concentration of the products, raised to the stoichiometric coefficients divided by the concentration of the reactants raised to their stoichiometric coefficients. So let's say we have AA plus BB is in equilibrium with CC plus DD, where of course the lowercase letters are your stoichiometric coefficients and your capital letters are of course your substance. Okay, we're going to learn how to write the equilibrium constant expression for this particular equilibrium. Now, one thing that I have to emphasize is solid and liquid phases are not represented in an equilibrium expression. Now, we're going to assume then, for this particular reaction, everybody, that these are either gases or aqueous phases that are present for our reactants and products here. So, when we're writing this, we're going to say the equilibrium constant K is equal to capital C raised to the lowercase c power times capital D, the concentration of D, raised to the lowercase d power, all over the concentration of A raised to the lowercase a power times the concentration of B raised to the lowercase b power. And that would be my equilibrium constant for this particular equilibrium. Again, only gases and aqueous solutions are represented in the equilibrium expression. Super important there, guys, because if we saw a solid or a liquid, I would no longer include it in this expression. Okay. Last point is this. What allows us to write that, guys, is the law of mass action, which is simply the relationship between a balanced chemical reaction and the expression of the equilibrium constant. So the law of mass action allows us to write the equilibrium constant K is equal to the concentration of C raised to the lowercase c power, times the concentration of D to the lowercase d power all over the concentration of A to the lowercase a power times the concentration of B to the lowercase b power. All right, that's what allows us to write that expression. Let's continue on. So I want to write the equilibrium constant expression for the following chemical reactions. So let's pick up with our example problem that we talked about at the beginning of this presentation, which is, of course, H2 plus I2 is in equilibrium with 2HI. So if I'm going to write this expression, I'm going to say, okay, well, the equilibrium constant, capital K, is equal to the concentration of HI squared over the concentration of H2 times the concentration of I2. Okay. And then number 2 is we would have the equilibrium constant K is equal to products over reactants. So we're going to have CO the concentration of CO times the concentration of H2 squared. Okay, again, I'm just raising my concentrations here to my stoichiometric coefficients of my balanced chemical equation, all over the concentration of CH3OH. Okay, and that would be my equilibrium constant for number 2. Now, very important example here, guys, I'm going to star this, is you must have a balanced chemical equation to write the equilibrium constant. Okay, so that's super important, guys. Make sure you copy that in your notes. Moving on. All right, this is a we review problem. So I want you to write the equilibrium constant for the following chemical equation and then check it with my work. Alrighty, and I hope you were paying close attention, everyone, that you have to balance the chemical equation first before you can write the equilibrium constant. So I balanced the chemical reaction with the coefficients 1, 5, 3, and 4. And then once I wrote my equilibrium constant, I got capital K equals the concentration of CO2 cubed times the concentration of H2O to the 4th power over the concentration of propane, which is C3H8, times the concentration of O2 to the 5th power. Okay, so that would be my equilibrium expression for this particular reaction. Now, the one thing that I want to just pose as a hypothetical is suppose the water was actually H2O liquid instead of steam. How would this affect the equilibrium constant? Now, if this was the case, right, if water was a liquid instead of a gas here, guys, our constant would just be this. We would say, okay, well, then it's just the concentration of CO2 cubed over the concentration of propane times the concentration of O2 to the 5th power. You'll notice what happened is I eliminated my concentration of H2O because if it was a liquid, liquids we don't represent in the equilibrium constant. So that's how it would change. Instead of it producing steam, if it produced liquid water, we would just omit the concentration of water. And let's continue on. All right, so the significance of the equilibrium constant. Let's talk about it. So when the equilibrium constant is much, much less than 1, then the reverse reaction is favored, which means the forward reaction does not proceed very far. If the reaction constant K is approximately 1, then neither direction is favored. The forward reaction proceeds about halfway. And finally, if the reaction constant K is much, much greater than 1, then the forward reaction is favored. This means that the forward reaction will essentially proceed to completion. Okay? Let's talk about this conceptual problem, which would be evaluating the significance of K there. So it says the equilibrium constant for the reaction A is in equilibrium with B is 10 point. Okay. A reaction mixture is initially contains A at a concentration of 1.1 molar and B at 0 molar. Which statement is true about the equilibrium? So we have 3 cases with our equilibrium constant. Case 1 was when K is much, much less than 1. We said that the reverse reaction is favored. Okay. So the forward reaction then proceeds very little. Right. That's what we said. When K is approximately 1, we said that neither direction is favored. Okay, the reaction proceeds about halfway. And then finally, the third case was when K was much, much greater than 1. We talked about that when K is much, much greater than 1, then the reverse reaction is not favored, so the forward reaction is favored. My apologies, everyone, for saying that backwards there. So in this case, we have 10, which is much greater than 1, and we have to find a condition that would represent when the forward reaction will essentially react to completion. So what we're going to be looking for here is a case in which there's a high concentration of B, but a low concentration of A, because again, A is decomposing to form B, right? It's in equilibrium with it. So we look at step 1, we have a high concentration of A, but a low concentration of B. That can't be it. In B, we have a low concentration of A, but a high concentration of B. So this is going to be it because, again, our K is large. It's larger than 1. If it's larger than 1, the forward reaction is favored. If the forward reaction is favored, it's going to react to completion. If that's the case, we're going to have a high concentration of product and a low concentration of reactant. Okay? C, the equilibrium mixture contains equal concentrations of A and B. That would not be the case, right? That would be the case if K was approximately 1, all right? But not for this one. So the correct answer is B. All right. Relationships with the equilibrium constant, and then we'll be done. So it says if we reverse the chemical equation, you invert the equilibrium constant. So let's take a look here. So if I write my equilibrium constant in for the first reaction here, we would get the reaction constant K equals C cubed over the concentration of A times the concentration of B squared. Okay? Now, you'll notice, guys, that I also wrote that for number 2 because in the second case, the equilibrium constant, it's the same reaction, so I wrote it for both cases. But let's talk about when we invert. So this, by the way, would be called K of the forward reaction here, because in C, I'm going to write K for the reverse. So K for the reverse is, since I reverse the reaction, I'm going to invert the equilibrium constant. So instead of it being C cubed over A times B squared, we're going to get A, the concentration of A, times the concentration of B squared over the concentration of C cubed. Okay, so again, for that relationship, all I did was I inverted the equilibrium constant, or I took the reciprocal, however you want to think about it. Number 2 says, if we multiply the coefficients in the equation by a factor, we raise the equilibrium constant by that same factor. So if you guys take a look here, between A and B, I rose the factor of A by a factor of 2. So that's what I'm going to do for our new equilibrium constant. I'm going to call it K prime since it's a new one. It's not the original K. It's slightly different now. So if that's the case, my concentration of C, I raised my A to B by a factor of 2. So 3, I'm going to raise to the 6th power. A, I'm going to raise to the 2nd power. And then B, I'm going to raise to the 4th power here. Okay. Again, I raise my equilibrium constant by that same factor. I raise the entire chemical equation. So K prime here would be slightly double with all my coefficients. My exponents that I'm raising it to will be doubled. Okay. So that is the first two relationships with the equilibrium constant. Let's talk about the last one. Final one is if we add 2 or more chemical reactions together to obtain an overall reaction, then we multiply the corresponding equilibrium constants together. So let's write the reaction, the equilibrium constants for both. So I'm going to call A is in equilibrium with 2B, K1 is equal to B squared over the concentration of A. And then I'm going to say K2, the second equation here, is equal to C cubed over the concentration of B squared. And now when I want to get my K overall, what I'm going to do, guys, is I'm going to multiply K1 times K2. So when I do that, I'm going to have the concentration of B squared over the concentration of A times the concentration of C cubed over B squared. You'll notice that the concentrations of B squared cancel each other out. And my new equilibrium constant, my K overall for my third equation, is the concentration of C cubed over the concentration of A. And that is my new equilibrium constant for my third equilibrium reaction right here. Okay? With that being said, guys, I'm going to end the video here. Be on the lookout for a part 2 of this video about just plugging numbers in to some example to run some numbers with the equilibrium constant itself. You'll notice we have in this video only just written the equilibrium constant. We're going to talk about when we actually have to crunch some numbers in the next video. So the next video shouldn't be too long. That being said, guys, have a wonderful day. I'll see you in class.